Hello, I'm Justin Harrington, and we are going to be talking about today our research question with a group of Colin, Hughston, and Kushal and myself. Our research question is understanding which pitches work better to obtain desired events. We looked at which pitches over the last 5 years, 2015 to 2019, caused the most strikeouts and caused the most double plays. The idea is to understand which pitches work better in those situations, and through this, we can understand which pitches we should avoid in different scenarios and which pitches we could throw in a certain situation. So I'm going to start off and tell what packages we used. We used Baseball R, Tidyverse, ggplot2, Shiny, ggRepel, dplayer, Layman, and Shiny. Shiny's there twice. We use all of these. The Baseball R is to scrape here, as you can see. The Tidyverse is to clean things up. The ggplot is to plot later on in the presentation. Shiny is to plot again later on in the presentation, and everything else has its spot, and it will be used throughout the presentation.
All right, so I'm going to talk a little bit about the data we obtained right now and how we obtained and what we did with it exactly. So to scrape the data, we use the scrape statcast savant underscore pitcher all function that we obtained from Baseball R, and this allowed us to basically scrape all the pitcher data from two certain dates, and it gave us all the data between those 2 days. So we wanted the 2015 through 2019 seasons, and we did it on a monthly basis. And the reason for this is we can't run a large amount of dates in between using this function, as my computer couldn't handle it. And that's why we can see here that April of 2015 was broken into 4 segments, and then after that we bind them together in April 2015. And then we repeated this process for every month of the MLB season, so you can see April through September. And then what we did is we then binded them all together to find 2015 data. And we did the same for 2016, 17, 18, and 19. The reason why we structured it in such a way is that it makes it easier for us to work with, and it also makes it easier for us to understand and debug code if there was an issue. So once we repeat that through, we have 20. Here we go. We have 2015, 2016, 2017, 2018, and 2019, and then we binded that all together to make our data set. And rather than running this scrape every single time, we wrote it as a CSV. And the reason for that is also because we can then we can work on it together rather than have every single member of the group scrape it all. Moving on, we then had to clean up and filter the data, make it usable. And in order to do that, the first thing we did is we filter out the pitch types that contain the following numbers in them. So pitch type in this database was what type of pitch was thrown. So it could be a changeup or a fastball or a curveball whatsoever. So if there was a number like this, then it wouldn't make sense. Hence, we use the grepel function, which basically would delete the cell if it contains the following text, which is 160421. And the reason we use these two lines of code here, which I've highlighted, is because that we found out that a lot of the cells that didn't have the pitch type would have a number like this, one of these two numbers followed by another few numbers. And hence, rather than making it extremely repetitive and going through each and every single cell and deleting it or writing out code for each and every cell, we could simply use this function to delete all of them that contain this number. And it worked out for us because all the pitch types that were in the form of numbers contained these two numbers. Then the last thing we removed is null, which was basically when the pitch type wasn't there. This also helped, as it would help clean up the data and make it useful. So once we did that, we also then filtered the data into subsets that we could use for our regressions or our visualizations. The first one I want to talk about is strikeout data. And we basically filtered so it's only in the events of a strikeout. So that helped us determine strikeout pitches and work with that data. The next thing we did is 2 strikes, which is basically the data of pitches thrown when the count already had 2 strikes. This made it easier for us to figure out, what pitchers tend to throw when they can have the opportunity to strike out a batter. And then we also did double play data, which is basically when the event was a double play or the event was he was grounded into double play. This helped us analyze what was happening on the pitch when the double play occurred. We also created two more data sets that added a column. So this one is strikeout binary. The reason is we added a column that was called strikeout, and in this case, it just gave out ones and zeros for when the event was strikeout. And the reason we did this, we then filtered this data out so that it only had instances when there were two strikes. That means the pitcher had the opportunity to strike out, and we want to see when a pitcher has the opportunity to strike out a batter, how often does he does that? And we can use that with this logical ones and zeros, and we eventually use this in our regression in the future in the code below. And then we did the same for double play binary. We created a column that called double play, and it was basically ones and zeros if the event was a double play. And then we filtered out when if the batter appeared and the outs went up was 2, we filtered and took those rows out of the data. And the reason for that is because if there were 2 outs, it would be impossible for the pitcher to have a double play, irrespective of how many people are on base. In the future, we hope that we can have data where we already know that one person is on base, and then we can filter out that way. However, we weren't able to do that with this data set, so that's something we can look for in the future.
So after we filtered and reformatted our data, we wanted to see two plots of which pitches were causing the most double plays and strikeouts on a year-by-year basis. So if I run this code chunk here, the plots will have year on the x-axis, and the y-axis will be a count of the number of strikeouts or double plays a pitch caused. Each line is separated by a different color based off of its pitch type, and I saved these earlier as PDFs. So we'll see the double plays per pitch over time. The top 2 pitches have both kind of been decreasing over time and how many double plays they cause, with 4-seam and 2-seam fastballs. Pitches that have been on the rise in the second tier were the change-ups and sliders, with sinkers starting to decrease in how many double plays they cause. And then the lowest list of pitches that are commonly thrown are the curveball and the cutter, and then there's another grouping of less commonly thrown pitches towards the bottom. And then to view the strikeouts per pitch over time, once again, 4-seam fastballs are at the top, and they have been causing more and more strikeouts over time. Same with sliders right below as the second most strikeout pitch, also have been increasing over time. Then the second tier is changeups and curveballs, which have also been slowly increasing the number of strikeouts they've caused over time. And then there's the lowest grouping of pitches with 2-seamers towards the top that have all kind of stayed constant over time in how many strikeouts they caused each year.
Now I'm going to be talking to you guys about a second set of visuals here. So we start off with a plate width visual and a K-zone plot visual that allows us to later on run visuals within a strike zone plot. We jump right into filtering our double play data to count each pitch type. So we do this, and each pitch type is then counted the amount of times that it occurs within this double play data right here. And then we change the n to number of pitches, and we end up with something like this, where each pitch type is laid out, number of pitches laid out. This is from 2015 to 2019, like the rest of our data. Then we're going to jump right in here, and we're going to make a bar plot of double play pitch type. So right here you see the amount of times that a pitch caused double play, 2015 to 2019, and each pitch right here. So by far and away, 4-seam fastball takes the lead. So after this, we're going to go into where these pitches took place within the strike zone. When we run this, we get something that looks a little bit like this right here. So this is pitch locations for double play pitches over the last 5 years. These are where these took place. As you can see, it's kind of tailored more towards the bottom of the strike zone. With, again, if you could see this color right here, 4-seam fastball being the far and away leader. So we're going to do something similar with the strikeout plots. So we do the same thing where we count the pitch type, count each pitch type within the strikeout data over the last 5 years, rename n to number of pitches, and this time we tried something where we made a pitch percent, which is the number of each pitches divided by the total observations over the last 5 years. So this is the total amount of strike zones over the strikeouts over the last 5 years times 100, so we get a percent. And then we add that back to count Ks. We're going to get something that looks like this, where it's each pitch type, number of pitches, pitch percent. Again, far and away leader here. Four-seam fastball at over 30%. Second place, we got the slider here. So when we do that, we go ahead and run this again, and we're going to see this is the amount of times it's pitch called a strikeout over the last 5 years, where we got four-seam fastball here. Slider is second. In the double plays, we saw this pitch right here being second. So obviously it differs as they are different outcomes. And then we're going to run this again with the strikeout pitch locations. And like we said, we saw that the double play was kind of more centered towards the bottom. Here on the strikeout, we see a lot more out of the zone, random, definitely a lot more up top right here. I think that goes to show when you double plays, a lot of these are ground outs to second base, shortstop, and they turn two. Where a strikeout is you get them to chase and they swing and miss.
So the next thing we decided to do was to run regressions to figure out which pitches were most successful in getting strikeouts and in getting double plays. The first regression uses the strikeout binary data and uses the strikeout variable as our dependent variable with each pitch type as our independent variable. And then this will figure out which pitches are most likely to result in a strikeout and least likely to result in a strikeout when there are two strikes already in a count. A positive coefficient means that they're more likely in causing strikeouts, and then negative means that they are less likely. The most statistically significant positive pitches, so the best strikeout pitches, were found to be curveballs, ephus curves, splitters, knuckle curves, and sliders. The least effective pitches in getting strikeouts with two strikes in the count were four-seam and two-seam fastballs, knuckleballs, and sinkers. The next regression does the same thing, but for double play binary data. And once again, positive coefficient results in more double plays, negative means less double plays. So our best double play pitches that we found were the two-seam fastball, the scurve, and the sinker. And then the pitches that were the worst at causing double plays were curveballs, four-seam fastballs, splitters, knuckle curves, and sliders. And then the regression results are posted here below.
Alright, so now I'm going to talk a little bit about some of the visualizations we made after our regression results. So one of the first things we did is we wanted to look at the pitch types that impacted a strikeout or a double play, or the events we looked at in a positive way. And we looked at those pitch types on the strike zone above the plate. So if we look through our code here, we first then create the image of the plate and the strike zone. And then we filter out our strikeout data for only that pitch type. So here you can see we make zone data curveball as strikeout data filter out for only curveballs. And then we use the plot we made earlier, add in that data, and eventually make out our strikeout zone. So here, if I run this first part of the code over here, right, here you go, and we can see then the plot of it. And as you can see, it has similar to an upside down U shape, kind of like that, and where the bottom part is a lot wider, which shows that curveballs that move a lot, that get down low in the zone, are striking out people, probably because they're convincing batters to swing, and that's probably more of the reason. And that's why it's a lot less of a probability of a higher curveball to cause a strikeout. So now when we run through all of this entire chunk, we can look at every pitch type, and I'm going to discuss the graphs for each one and the results. So if we run through them, right, it's all repetitive code of the same thing, just changing for the event or the pitch types. Like for double play, we change it from strikeout to double play. But otherwise, it's the same structure of the code, just changing a little bit based off the pitch type or event we want to look at. And that should create about 8 visualizations down here. So let's start from the left, and we can see strikeout for a curveball, as I discussed earlier. And then this is the ephus. So there's obviously a lot less ephuses thrown, and that explains why it looks a lot less cluttered than the curveball. Um, However, you can see with the ephus again that most of it is down low in the zone, right where the mouse is hovering. And I think that makes sense because one, it just has that more movement when it gets down low, I feel, and that convinces the batter to swing and miss. Now, if we go next, the next one was the split finger. And again, you can see that there's a lot more heavy of color down low rather than up in the zone, showing that lower in the zone is always better in this case, probably because it's more movement based. And then the knuckle curve, again, very similar to the curveball shape, a lot less in quantity, obviously, because I feel a lot less pitchers throw a knuckle curve in terms of a curveball, but it has the same structure, the upside down U I talked about earlier. And then the slider. The slider, you can see, is just a lot of them have been used to strike out batters in the last 5 years, and it's just a lot more has been down low. This area right here, down low, significantly more than the ones up top, and that's probably because of the movement down low, and also that's harder to hit a ball that's lower in the zone or outside and low. Then we look at double play ball. So this is when the ball, the swing or bat results in a double play. So you can see the sinker when it gets right in the zone, it's probably moving downwards so it reaches the bottom of the bat, resulting in a ground ball, making it easier for a double play. So the screwball, which was considered significant, were only 2 pitches were there, so it isn't accurate or fair to make any judgment based of that. Hence, while we still graphed and looked at the regression result, it's not fair to make any sort of judgment from this. And the last one was the 2-seam fastball. This again, it looks a lot more inside the zone actually working, and it's a lot more cluttered in you would say the bottom right zone or right here where my mouse is, and that's what works for these pitchers and throwing it in there. So that's what these graphs do. Now, a few similarities we want to point out is a lot of these are always down low. The down low pitches work a lot more better for the strikeouts, and these are all pitches that move downward, you could say. So that's a huge thing we should definitely look at in the future. And then for double play balls, the two that are always in the bottom right or the bottom half of the zone are more of an intensity down low. So those are the 2 things I think that we should look at and focus on when we figure out or do further research on this stuff.
All right, so that leaves us with part 8, the last part of our project, and this is all about Shiny. We tried to make a bit of a Shiny app using one of our graphs. And so this is the part that I really worked on. And the thing I wanted to really dive into here was evaluating how weight plays into double plays. I really wanted to look at this because I wanted to get an idea of what kind of role speed plays in it. And so obviously weight's not a perfect indicator of that, but generally guys who are heavier, they're going to run slower, and vice versa. And so what I did here with the code was I took our big data set and I paired it with master data set from Layman, which I paired with this CSV from GitHub that has a lot of information about players. It actually ties into one of our earlier homeworks, I think. But it's really helpful pairing it, and you can get stuff like weight, height, college attended, deaf, spouse, all that stuff. So anyways, made that into a giant data set, and then I ran that through the user interface. We decided to use a slider panel, just evaluating the bin size and all that to change up the graph a little bit, and then plug that into the server, ran that. I won't actually run it right now because it takes forever to load, but I do have it running in the background. And so this is what it looks like. You can drag this up and down, make the bins shorter or smaller. But anyways, this is the distribution. And so I thought this was kind of interesting, to be honest, because it's a very normal distribution, and I was really expecting there to be some kind of effect for body weight for how many ground balls you play into. But this is really, I think if you had a graph of the spread of body weights for baseball players in the MLB right now, this would look pretty similar to that. Obviously, I think the average is like 207 pounds, something like that. So this is really kind of right around it. And what I can kind of come up with as to explaining that, I think that really this is an indicator of just how much the game's been optimized in these last couple of years. When you look at power hitters nowadays, they're the three true outcome kind of guys, you know? They've trained, gotten their launch angles perfect. They've learned which pitches to hit and which ones to lay off of. And so their game is all entirely predicated around hitting the long ball, hitting balls into the outfield. And so I think if you look at their ground ball totals, they're going to be a lot lower than those of some of those middle or kind of tweener guys, you know, that make a lot of contact. And so I think that just kind of really translates well to balances out. And then I think somewhere in the middle ground is where you see that peak, where you have guys that can do a little bit of both. And so they don't really have just one thing they're aiming to do when they get up at the plate. And so I think that might be part of it. It also just might be that there's not that many guys that weigh, 170 pounds in the baseball, and not that many guys that weigh 250 plus. And that it is a very tight, spread. And we can change this up a little bit, put this at like 24 or whatever. But we also have this colored based off of pitch type. And I think that ties in well with our original project goal, which was analyzing the effect that pitch type has in some of these situational baseball outcomes. And so I think this really kind of ties in well with what our project found too. Looking back at our model, we found that, two-seam fastballs were significant, and those are still significant here. Obviously, four-seam fastballs are really going to kind of make most of the double plays, and that's just because they're thrown so often. But I think the two-seam fastball is really kind of a more specific pitch, especially when you have so many guys that throw sinkers, splitters, and all that, and we can really tell the difference with the data set that we have here too. And so I think if you look at the percentages of two-seam fastballs thrown in baseball, there really shouldn't be that much, but they're still accounting for a lot of ground double plays here. And so I think that kind of tells them that there is some effect with the pitch type that you throw. And obviously it's not a catch-all situation where you can just throw only two seams and you can never get hit and all that stuff. And I think it really lies in somewhere of a balance of mixing your pitches, knowing when the situations to throw them, how you disguise them, how you pair them with other pitches that you have in your repertoire. And then also just like velocity, movement, and stuff like that, the pitch design of the pitch. You can't just throw a two-seam and then have it not move and expect the result. But I think this was an interesting project to kind of see how it all played out. And I know that I enjoyed it. I think I speak for the rest of our group and that this was really kind of fun to work with. It's cool to see how much data we could really gather. I think if I had more time, I honestly would like to look at the effect that batter-handedness had on this. I don't know. I'm kind of interested in what switch hitters can do. I think that, having the benefit of hitting from both sides of the plate, you can start to get a different viewpoint on certain pitches maybe, how the ball moves. I don't know. That would have been something that I would have been interested in looking at with a little more time. Obviously righties, lefties, and all that, but I think there's just so much that you could do with this, and there's so much data that you have at your disposal, which really makes this a lot of fun. But anyways, any thoughts and questions? We'd love to hear them, and yeah, thank you for your time.